Hello, everyone. My name is Rivera, and this summer I had the pleasure of working with Professor Silly Deng and So-Young King in the Department of Mechanical Engineering at Penn State in a project where we tune the performance of energetic materials via architected channels. So, what are energetic materials? Energetic materials are materials which produce large exothermic reactions but also have tunable combustion performances. Because of this tunability, they are used in many different applications in the world today. One of these is pyrotechnics, which are fireworks, and the others is solid propellants, which are used in satellites and rockets in the world today. So why is this tunability important? So these tunability of energetic materials helps us evaluate and examine the physics behind these combustion reactions. But how do we achieve this tunability? Recent studies have shown that pattern engineering designs give insight on these heat transfer mechanisms and achieve this tunability. A very, 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 very important finding was that convective heat transfer in pattern pores increases the burning rate, which lets us to believe and lets us to question how exactly can these pattern designs affect the performance of these combustion reactions. To answer this question, we believe that the material consumption rate increases with minimal channel distance via convection. To prove this, we used the 1D setup to simplify our results and findings and experiment with a channel gap size between 0 to 500 micrometers. We believe that a minimal channel distance will increase the material consumption rate, but as the channel distance increases, the material consumption rate will decrease. To prove this hypothesis, we used a method where we first formulated nano-aluminum, nano-copper oxide, and PVDF HPMC, which are two solvents, solutions, where we then use this solution in a 3D printer to print two 1D samples with the microchannel gap of 10 micrometers and the macrochannel gap of 500 micrometers. We then set up the samples in the imaging system to perform the experiment, where we then ignited them and collected the data and snapshots of the ongoing combustion reactions. So through the imaging system, we were able to get the different snapshots of the combustion reactions while they were happening, and we found very different and interesting things. So for the fully dense energetic film, we can see that there's no channel gaps in these flame propagation and the burning front of this material. You can see a uniform flame propagation between right to the left. In the microchannel gap, we see that there are microchannels, right? We clearly see the black spots in between the flames, which lets us know that there is hot air in between those channels. In the macrochannel gap, we can clearly see the hot air penetrating the channel first and then spreading the flame through the dense energetic film of this part of the setup. So through these snapshots, we were able to calculate the material consumption rates, and we were able to see that the microchannel gap produced peak performance, right, and produce a higher material consumption rate than the fully dense energetic film and the macrochannel gap. But we were able to still see that the macrochannel gap still increased the material consumption rate. It was much lower than the microchannel gap, but it was much higher still than the fully dense energetic film. So from this, we concluded that the combustion performance of these pattern structures are definitely tunable, but that the microchannel gap lead to peak performance and lead to a higher material consumption rate when compared to the fully dense energetic film and the macrochannel gaps. So for the next steps with this would be to manufacture more pattern designs and perform combustion reactions with these designs. And then in the future, be able to create a model to help predict these heat transfer mechanisms and burning rates to then use in industry and for more research. All right. Thank you, everybody.